Do you need to write this? No. What you need to do is, you just need to know which one is relevant to your case, right? You don't have to rewrite it in your paper and then you scratch it there. I don't need that. But this one. In fact, from this one, you only need this one. You don't need these two. You only care about this. So you have this one. Since now u is only a function of y, so you convert it from PDE into ODE. By having that, you can double integrate it, because now if I move this into there, or I rather move this one, dpdx into there, it becomes positive, right? So you have dpdx mu d square u dy squared. Okay? If you have that, so you have mu du dy squared equal to dp dx, or you can just move that mu into the other side, become 1 over mu dp dx. Okay, if you have understand, please bear with me a little bit more before we can run. Now it's still warming up. Okay, we will run marathon. Okay, so now you can double integrate it. First integration, because it is integration towards y, so there is nothing you can do with dpdx. It will be a constant. You get y there, you get c1. Where did c1 come from? Because this c1 is a constant. When you take the derivation of it, it will be gone. So it has to be there. Same goes for c2. So when you double integrate it, you will get c1y plus c2. Okay, I think there is no problem until this point. Or is it? Are you clear now? Okay, hopefully after this, no more question about how you get this. Now the other question that I get this morning is how to get C1. Oh, sir, you suddenly got C1 and C2 become 0. I do not know where it is come from. Okay, let me explain to you again now. You know the boundary condition that bounded this flow. You don't care about the inlet and outlet, right? Because the flow is not a function in x direction. You don't care the side wall, both side wall, because u is not a function of z. It's only a function of y. So you need to know the boundary in y direction. So in this case, the flow is bounded by two parallel plates. Since it is stationary, whenever the liquid touches the surface, it will have the velocity of the surface, in this case 0. Okay, remember that. Because in the second flow scenario, you will find the top surface moving. So that's the only difference. Okay, but this one will still be the same. That is why this one is very important. If you have any question, ask now. Okay. So you have at y equal to 0, your u is equal to 0. At y equal to h, u equal to 0. Clear until this point? Okay, if you are clear until this point, you can go here. Now, you put u equal to 0 when y equal to 0. So you plug in, you get this one equal to 0, this one equal to 0. So C2 got no option but saying, oh, I am 0. Right? So in this case, C2 is equal to 0. Is it always true? No. Okay? At some point, I can give a boundary condition that the bottom plate is moving towards the left at velocity of u. What will happen if I do that? This become u, 0, 0, so C2 become u. That can be happen also. Okay, that can happen. It depends on your lecture actually. Or depend on you, if you make your own question. Okay, so this one become 0. Since C2 is 0, so you don't have C2 anymore. So your u become 1 over 2 mu dp dx y squared plus C1y. Okay, so that's the solution now. Because C2 you know it is 0 for this case. For other case, different. Since your C1 is unknown, so now you implement this at y equal to h, u equal to 0. Simple. You put 0 here because this one is u. Then you put y as h. Right? You put h there to replace the y. Now you can see, because this one is 0, I can move this one into that side. Now I get C1h. Right? I do not want C1h. I want C1. So what I will do? I will move this to that direction, right? So h squared divided by h become h. Is that clear now? Okay. So you get C1 equal to minus 1 to mu dp dh h. Is that clear? Okay. So once you have that, this one is not your final version, right? Your final version is this. So you just put this one back to that. So that's what I'm doing here. So you don't have to worry about this. If you end up with this one, that's perfectly fine. In fact, I do not recommend you to do this. I rather have that one, right? Because then it is still clear, right? This one is your main. This one is your C1. Maybe you will have another C2, right? So it's perfectly fine if you stop with it. That's it. No problem. Okay? Clear? So having this, you can start to find your Q, you can start to find your Umax, you can start to find your Umin. You know all those things, right? If you want to find the Umax, you need to find the Y. Where U is maximum. How to get that Y is by setting du dy equal to 0. So from here you will get the so-called Y max, the location where the U max occur. Once you get your U max, just plug into your U. Then you get your U max. Okay? Don't think that from du dy you will get U max. No, it will not give you U max. It will give you Y max. Or the location where the maximum velocity occur. Right? Once you get those locations, you can just simply plug into your U equation and you get your U max. Okay? That is for U max. If you need to find U min is nothing but your Q over H. And those Q is nothing but U dy H. This is it. So it's really a simple story. Once you got your U, you can play around with it. And then sometime, I try to challenge you to find tau. But tau is nothing but mu du dy. So basically, if you know how to do that, you know how to do this. That's that. Okay? Clear now?